Okay. So today, what I just want to do is just to kind of like give a little bit more context for some of the stuff we were doing last time. About last time what we did was kind of like you had this joint probability matrix, and you took the square root of all of the entries of each entry, and I called that like an amplitude matrix, and we did like an SVD that. Uh, But I'll kind of like actually give a little bit more context of why would you do that. Um, and then so it's a bit more motivational today's class. And then next week we'll actually do the SVD for tensors, and then we can do like the applications. So like the only thing left is of like kind of like go over like how to apply like a similar validated into tensors, which will give us like the tensor trains. And once we have that in place, then we can kind of like keep that for interesting things. But I did want to give some explanations today. And let me see if I actually wrote down any book. So yeah, like last time we had like a joint probability matrix. And what I had told you is like, well, what if you take the square roots of the entries, right? And this, I mean, for um, not so secret reasons, like that's what I call like, oh, you can call it like an amplitude matrix if you want. So this is what usually you refer to as the joint distribution. And this would be kind of like an amplitude matrix. And then what I said is like, well, if you happen to do an SVD, if you try to do like an SVD for the amplitude matrix, right, you have to consider A and A transpose, right, or A transpose A. So you for like the SVD, you consider. And I mean, I'm not going to repeat what happened there, but the idea is that if you kind of like remember, I think I had done it for A transpose A, but like a similar formula works in the other case, is that along the right, like each of them are square matrices, and the idea is that along the diagonal, you could read off the marginal probabilities. That's kind of what's like the nice thing about doing it this way, right? So on the diagonal, you have like the marginal probabilities. Now the marginals, remember, the marginal is just kind of like what you get if you kind of like take the rows or the columns of the matrix of the joint distribution and add them row or column wise, depending on which one you're talking about. So it's essentially like a marginal probability is what you get by forgetting stuff, right? It's kind of like an erasure of information. You keep less information. Um, and then outside the marginal, outside the diagonal, you had stuff. I mean, was like the complicated formula, so I won't write it again. But you had stuff that had to do with like this conditional probabilities, kind of like this Bhattacharya coefficient, like, but it was something involving conditional probabilities, involving involves conditional probabilities. And in the matrix is symmetric, so like this would also be the condition. Okay. Uh, so these, I'm going to kind of explain a little bit like the context for doing it this way. Yeah. For last, I think we had 4 by 4. No, it was like the matrix was 3 by 2, and so like the two options were two.
No, that.
Yeah, that ended up being 2 by 2. Yeah, it was 2 by 2. Yeah, I can go to the notes actually.
But my question would be is like.
To like find out what that would give you. What happened here? Let's see. Let me share again my. Okay, so yeah, no, like I'll mention like I'll put that as an exercise just to work out what you get on if you do A transpose. So you get marginals, but even there, like the marginals that you get are for the other features, right? Like these were like I think food, fruit, and vegetable. The other ones would be for marginal being red, marginal being green, marginal being purple, and outside the diagonal, then you get like these PC coefficients, but of different conditional probability. No, but yeah. So, but it's like a fun like formula to try to figure out. Okay, but yeah, like what I was going to explain a little bit today, it's kind of like some context so that it doesn't seem like such an artificial construction. Now, just to kind of like have like a notation, a slightly useful notation. So, and another way to think about the joint distribution, right? So you could imagine, here's one way to do it. Like you could have two people, which I just follow the convention, I call them Alex and Bob. So you have two people, so. And I'll assume that each one has a coin, right, that they could flip. Each has a coin. Okay, and so the outcomes for like, and so Alice, like her coin could land on heads or tails. I'll call them HA and TA for heads, tails of Alice, right? So the A just for Alice. And then Bob can also has his coin and then it lands on you know heads or tail, right? So you can think of this like I'll think of Alice. I'll call X. I'll call X the like the outcomes that Alex could get, and I would call Y the outcomes that Bob could get, right? So if you do the Cartesian product of those two sets, right? You know, it just gives you the four possibilities that you would expect. Right? And so if you have like a probability distribution for X times Y, right? Basically what it does is, like it just like assigning of probabilities to those four events, right? It's like a function of, Bij, like, like it's kind of like the same notation as before. It's Bij. But now I and J, let's say, goes from 1 to 2, right? If you kind of like arrange them into a matrix. So like you could think of heads as being the first column, like, I don't know, like you could put it like this. So the Alice row is this way and Bob is this way. And then this is heads, tails, tails. Yeah. Right. So this is like the probability, that Alice gets an A, the probability that Alice gets heads, Bob gets heads, or like the probability that Alice gets heads and Bob gets tails, etc., right? So from that perspective, like the only reason why I'm changing to this perspective is just like from this perspective, kind of like Alice and Bob are the systems, right? And then extra X and Y describe kind of like the joint system, like like the total system, like. So in a sense, like X times Y describes like the combined system. And like X and Y are, like the outcomes Alice could get or the outcomes Bob could get are kind of like subsystems of like all that can happen, right? So, and the total system. For example, when you do like a marginal probability, right? Like, what is like the marginal here? If you, let's see. Hmm. Oh, let's do it this way, actually. Right, like what would this correspond to? That would be, the probability that Alice gets an, let me use like a bit of a more notation. This is a probability that Alice gets ahead, Bob gets ahead, plus the probability that Alice gets ahead. Um, sorry, this should have been Bob. The probability that Bob gets a tail. Right, so like what I was saying last time is that like basically you're adding over the two possible outcomes for Bob, which are heads or tails. Right, so this the only thing that remembers, is something about the probability that Alice obtains a head, and so that's why you would call this probability P of H A, right? So this is the probability of Alice getting a head. This is not different from what I was saying last time. I'm just putting it in a slightly different vocabulary. But like so, from here, kind of like what I want you to remember from what I'm about to say is that so when you have like the total system, usually in probability theory is described using like a Cartesian product, right? Like if you had like four people, each with their coin doing like the same experiment, then you can do like a Cartesian product of those four like sets, right? Like the heads for the first person, tails, like heads, tails for each person. You know. So in like in the traditional way of like doing the probability theory, right? So it's not that I want like to call it like maybe classical probability theory, but the idea is that if you have like two subsystems, if you have two subsystems, X and Y, then the total system is described using the Cartesian product, and the total system uses the Cartesian product, and the probabilities for each subsystem are obtained by marginalizing, right? Like by taking this sum, like where you sum over the rows or over the columns. Okay, and the probabilities for each system, for each subsystem, is like obtained by by the marginals, like finding the marginals. Which is like this sum, right? Over rows or columns. And then, okay, now here comes some motivation for what I was doing last time. So what happens, like, is that what I was doing last time actually corresponds to like, by last time I just mean like this trick of like, oh, let's take the square roots of the probabilities and then do this A transpose A, all this stuff. That actually corresponds like, in the way like in which like quantum mechanics like is probability. So that's kind of what I'm going to explain today. So they like just to kind of like give you like the analogy, since I've kind of like put it in a box and I'll then kind of like give you some basic ideas so that at least you have some context for where it comes from. Because a lot of the literature, if you open any paper on tensor networks or quantum computation, like, I mean, obviously, if it's a quantum computation, you cannot read anything if you don't know quantum mechanics. That's kind of like more clear, but if it's even on tensor networks, a lot of the ideas come from quantum physics. So you cannot really read much of it if you don't know kind of what's going on behind the scenes. So in quantum mechanics, like the idea so the idea is that if you have two systems, let me call that in a moment. But if you have two systems, then instead of sets, right? If you have two systems, two subsystems. So instead of sets, you use vector spaces. So you have to use two vector spaces. You use vector spaces. So instead of like having a set for like X and Y, you have to assign to each system a vector space. Okay. I'm calling the vector spaces B sub A and B sub B because of Alice and Bob. So like just imagine like, Alice has its own vector space and Bob has its own vector space. That's kind of like the idea. Okay. So the subsystems, each subsystem kind of comes with its own vector space instead of its set. And the total system, instead of being the total system described by a Cartesian product, it is described by a tensor product. So you are supposed to take the tensor product of those vector spaces. So the total system, what replaces the Cartesian product is the tensor product here. So the total system is described by taking the tensor product of those vector spaces. And what corresponds to finding the marginals, what replaces finding the marginals is what they refer to as finding the reduced state. So like the reduced density matrix, which is what I'm going to tell you about today, which is like a very fun idea. So the marginals, instead of like finding marginals gets replaced, is replaced by finding the reduced the reduced density matrix, which is kind of like the name that you give to that, or the reduced state, if you want. So it kind of like, again, maybe to make it into a table, in classical probability, so you have like sets, like in quantum mechanics, you have vector spaces. And then instead of Cartesian product, instead of Cartesian product, you use tensor products. And instead of finding marginal probabilities, instead of marginalizing, like if that's maybe if you want to turn it into a verb, you kind of find the reduced density matrices. So kind of like that. So there's kind of like a linear algebra counterpart, basically all the things that you do like when you are working with like traditional probability theory. Okay. And maybe just to kind of like, and this is maybe where I would start. So, and the other thing is that, what you would call like, the outcomes of the experiment, which are usually called like observables, and then in that case, the outcomes of the experiment. So, for example, like the outcomes of the experiment, like of Alice and Bob would be getting tests or tests, right? Which you can describe as 0 or 1 if you want to kind of think about it more as like in bit notation, like getting a 0 or a 1, which are kind of like so that those like the outcomes of the experiment in that case, they are described by symmetric matrices. Okay, so which are called like observables. And that's what I'm going to explain first. Well, I mean, I'm ignoring the fact that you have to use complex numbers, but I'll do it all over the reals. But it's kind of like the same idea over the complex numbers, like because I don't want the conjugates to make my life easier because all the applications for the machine learning to be over the reals. So I don't think there's no point in doing complex numbers if it's not necessary. So I'll give you a model for a qubit. Okay, so let's talk about a qubit. So a qubit, which is like the basic, most simple example in quantum mechanics for like, so which maybe some of you have heard of. I imagine most of you have heard of a qubit before. So a qubit is a system that can only be found in two different states. And I'm being careful with the word because I'm saying be found, not that can only be in two different states, which is a little bit different. So I'll explain what I mean by that. So it is a system can only in two different states. So for example, there's like this thing where like if you put like an electron, so you put like an electron, so this is going to be my name for an electron, and you put like a magnetic field. Yeah. Oh, is it frozen? Oh, sorry. What's happening here? Oh, give me a second. to all of you today. Okay, so we're not alone. Okay, sorry, give me a second to let me share again. Oh, perfect. Sorry. I'm glad. Thanks for noticing. Okay, so like you could have like an electron, and this is called like you apply like a magnetic field, like and I mean, not that I'm not going to get into the description of all what's happening there. I'm just going to tell you what like you're observing. So if you kind of like pass an electron through like a magnetic field, if you imagine doing this like for tons of electrons, what ends up happening is like the electrons kind of like and you put kind of like a screen where you can detect it, kind of like a detection screen if you want. So what happens is that, like you either like kind of like they kind of like accumulate in two spots, either up or down, like with respect to some reference axis, and then you pump. If it's detected up, it's called spin up. If it's detected down, it's called spin down. But all that I'm trying to say is that it has like you know, two particular outcomes, right? So it's goes up or down, okay? And then like if you, for example, had placed like the magnetic field, maybe like not in the z direction, but kind of like in a different direction, kind of like if you thought about what, like maybe that would be the x-axis direction, then on the screen, like instead of going up or down, like it would just go left or right, which I'm not going to be able to kind of like capture to. Let me see if I can capture this a little bit better. Instead of like being detected up or down, it would be detected left or right. But the point is that once you have made your decision of how you want to orient the magnetic field, it only has two possible outcomes. That's what I meant by defining two possible outcomes, right? That once you have like a particular configuration in mind, then it only and you could call this like what, right or left, I don't know, depending on how you orient it. Uh, yes.
You say spin, like you're referring to like the actual electron spinning.
Not really. I mean, yes and no. Like it's just like it's actually where like the theory gets very complicated. So originally, that's how they thought about the electron, kind of like literally was some sort of like spin, like a spinning having place happening. But it is a bit more tricky than that. So it is better not to have a particular visual picture of what the mechanism is.
It's more like angular momentum.
But it is related to angular momentum, yes. Like it is related to angular momentum, but it is a bit more complicated than just like saying, oh, there's like a ball that's spinning or something like that. So all of these things, like if you try to do like a diagram, you're kind of like doing it a little bit of injustice because like the visualization is always a bit limited of what's actually going on, behind the scenes. But yeah, like what it is related to angular momentum, yes. But like the details like don't concern us. It's more like it can just be like be found up or down or left or right. Like once you choose like your direction in space for the magnetic field, then you would have to possibly this kind of like align or respectively that axis. Um,
Is like the place where the electrons travel. That is like deterministic.
if you want to be kind of completely accurate, like so because if you put the tech, that's what happens in the double slit experiment. I don't know if you have heard about that one. But so what happens in the double slit experiment?
Oh, no.
Double slit, yeah. Is that like the way, if you try to put like detections to kind of like see through which slit the electron passes, then the behavior is different. Like there's no interference. Like, so like the behavior is very sensitive actually to how you decide to do the measurement. Like, it's like all a big mess. Like, I mean, it's very interesting, but it's very easy to just say something completely misleading if you kind of have like a particular imagination for what's going on. So all that I'm saying is that this is kind of like the most empirical thing you could do. Like, oh, you just did this, you found two possible outcomes, and let's not worry about what the inner workings are because that's not what I care about for the example. It's just to kind of like motivate what's happening. Yes.
To add on to that, I think one thing that I is like this is not the, like, you will have, because there's like an electron moving this way and there's a beam moving this way.
Mhm.
Then by the cross product, there will be like a displacement this way, which is like really the most displacement. But if we ignore that, like that's
Oh, I see
the,
what you're saying, yeah, yeah.
that's the major thing that happened. But if we like zoom in and like ignore that axis, this
Then
is like
like
an
the
additional thing. So this is like a small effect.
Right, right, right.
The actual displacement happens in the orthogonal direction.
Correct, right.
But this is like something,
The
like
non-
we have explanation for that.
Correct,
in the
right,
Lorentz
the
course.
non-classical
But
part.
for this, we don't have explanation. And as you said, we thought this was spin.
Right, 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 right.
We know that it can't literally be all spin.
Yeah,
there.
That's true. There are other
We don't know
degrees.
why it happened.
Yeah. No, I agree. So I'm just describing kind of like the quantum, like the
Yeah.
generally quantity part, quantity positive part. Okay. Yes. All that I'm like, okay. So here's okay, but I'm just telling you this is a motivation. So the idea is that because once you choose the direction, you have two possible outcomes. These are two possible outcomes. Then you assign a vector space of dimension two. So the dimension of the vector space is related to the number of outcomes that you could get. So to describe the spin part of the electron, right? Because there's like the wave function, is what you're saying. Like it's more complicated than just the spin part. But yeah, if you just describe, since there are two possible outcomes, you assign to the experiment a vector space of dimension two. So you assign to the experiment okay. And then the electron itself is represented by a vector in the vector space. So the electron is represented by a vector in this vector space. So there's a vector, like, and I'll use this Dirac notation, let's call it. So this is the vector which represents the electron. Okay, and for example, well, it's a vector space of dimension two, right? So you can write it in terms of a basis, right? So the idea is that there is a basis that represents, for example, getting like spin up or down. So like there is a basis vector, I'll put like an arrow like this. And that means that, this is like a vector that would always give you spin up when you do the magnetic field like going up. So this is like the vector that would always result in getting spin up. I don't know if I said this, but like the idea is like if you just do this like randomly, sometimes you find spin up, you sometimes find spin down. If you kind of like put it on and the other one is called spin down. So like, vector that results in getting down.
So the whole reason like we're using vector spaces to the bottom, vector spaces to optimally, wouldn't be able to use sets.
No, the thing is, I mean, obviously, a vector space, right? Is always a set, right? But you want to take advantage of the fact that there are more things that you can do in a vector space than on a set, right? Because in a vector space, you can add elements, right? Whereas in other, so yes, vector spaces are set, but I'm like saying, oh,
Makes it easier to operate.
even something better is happening because they're set with more structure, which is probably helpful. You know, there are more things that you can do in this particular set. And the idea is that, any vector, right? These two form a basis for the vector space. So any vector is a linear combination of those two vectors, you know. So this is like, a coefficient, like I'll call this coefficient times like the first vector plus a coefficient times the second vector, right? And then you can take these to be orthogonal. I mean, you can even take them to be orthonormal. Like you can take all these vectors to be orthonormal, actually. And not like, I mean, you can take this one to have length one. It can be taken to be like length one. So this is like a length one vector. And these are also length one, but also like the basis vectors are orthonormal. So like it's an orthonormal basis. And then Pythagoras theorem, right? Pythagoras theorem says that the length squared. I mean, because it's orthonormal, you can apply Pythagoras theorem, like just in the same way as you typically would, right? Like you have like you can draw it out, right? Like this is like the vector v, and then this is here's the spin up. I don't know. Let's say here's like this spin up vector. Here's this, the spin down vector, and then this is like the rescalings, right? So this is C0 spin up, and then this one is C1 spin down. Okay, and because they're orthonormal, like you can apply Pythagoras theorem. So that just says that the length square of this vector would be the sums of these squares, right? Again, in certain speculation where we talk like better different in the formula the same way. Like, otherwise you have to put the modulus, like square, but you can ignore that thing. Uh, oh, but it's in this spot. You have one equals the sum of two numbers. One equals the sum of two numbers. Each of them is non-negative, right? Because it's a square. Oh, so you have the sum of two numbers equals to one, right? So let's call them P0 and P1. Oh, and those are probabilities. And then this is actually the interpretation, right? Like the interpretation is like the length, like the coefficient squares, when you write down the vector as a linear combination, that gives you actually like the probability, that, the particular electron would go up or down when you kind of like measure like its spin. So these are like the probabilities. Uh, they are the probabilities that the electron would be measured either spin up And that's where like the name of the probability amplitudes comes from, right? Because they're numbers that square to probability. So these numbers in here are the one are called probability amplitudes, because it's any number that squares to a probability. So C0, C1 are called probability amplitudes.
So in our construction, like, we didn't assume that C naught, um, had head up and C1 head down is like an amplitude vector. So like, why should I not say that, why did we assume that the length of V is one? Like, why did we assume that like, um, the sum of C1 and C naught itself is one? Like,
Oh, it's just that.
like, why did we not say that the taxi cab like this?
Oh, and well, the thing is like, so I mean, what you're asking is kind of like a more like, important, like, philosophical question of like,
Yeah.
why do why?
Why did we make this stuff in it? Why didn't we like treat it normally? Like, why did we come up with this like probability amplitude form naturally?
Well, I mean, that is like,
Like, we just arbitrarily decided,
well,
what if we like have it as a unit vector?
well, no, like the unit vector. Okay, like what I should say is like, like the thing is like, you know, you know, the idea is like the vectors have to satisfy an equation, right? Which is like, called like the Schrodinger equation, right? This is a linear PDE, right? So what that means is that if you have a vector and you multiply, if you remember like the linear differential equation, sum of solution is a solution, and also like the solution times a number is a solution, right? So that's where the vector space comes from, right? Like the fact that you assign a vector space is because the PDE itself is linear. Then you have to put on top of that how do you compute probabilities, but that's kind of like called like the Born rule, but it is kind of like an extra assumption, but it is, what makes like quantum mechanics like the most predictive science of all, like it is the most accurate science like of humanity. But it's you're gonna do. I mean, difficult to try to justify it, but like I'm just putting it as a motivational thing, So I don't have to, but it's not like the
So the motivation was that solving the Schrodinger equation, gave us the vector V, which is
Right.
an element of vector space.
Yes.
And then like, almost out of nowhere, Born came in and it was like the amplitude squared will give us a problem.
Yeah. They
That's
kind of
like-
like, I mean, like, yeah, like the history is more complicated, but yeah, like it was not obvious, it is not obvious that that's how you would compute the probability by no means, but after like how the subject developed experimentally, you kind of realize that that's how it would work, and there were like many different like, and, historical facts, like, I mean, historical events that kind of like led them to the conclusion, but it's not that they started, oh, you have this linear differential equation, even the equation itself, like, took some time to find out. So it's not that you started with, oh, you have a differential equation, let me interpret, like the length squares as like probability, like this is kind of like what makes it kind of like genuinely, like it needs, like there's something interesting there, like that wasn't like before, the only, okay, okay, so I'm almost, so that's the first thing that I wanted to say. The other thing, is that, is bracket notation, which is actually useful to understand something that I'm about to say in a moment. But okay, if you remember, like the bracket, like I don't know if I said too much like about the bracket notation, but now I'm going to explain it a bit better. Which again is useful to know. in general. I'll be super concrete. So if I write something like this, by that I'll mean like a column vector. Okay. So this is called a cat. If I write something like this, I'll mean like a row vector. And in fact, in this case, again, because I'm working over the real numbers, I'll think about this as kind of being just like the transpose of the column vector. So it's just like the transpose of B. So like, for example, like, just to make it super concrete, if you thought that your vector is like, 2, -1, right? Like then if that's the cat, then the corresponding bra would be 2, -1 as a row vector. Okay, so it's like a fancy notation just for like transposing things. Again, if you work with complex numbers, then you have to conjugate as well, but I'm just kind of like explaining everything over the reals. Um, uh, okay, and then comes so this is a cat, this is a bra, and then a bracket is when a bra meets a cat, right? So what is a bracket? Which is like a fun way to write things out. So it would just be, if you had to, a bra and a cat, again, this just corresponds to a row vector, right? So if you want, let's just work with the vectors having 2 entries to make my life easier, just to explain the ideas. So what do you get here? You get Q1V1 plus Q2V2, right? Like you just get the inner product, right? So the bracket is the inner product. If you kind of like want to revert back to the original thing, right? No, the fun thing about, okay, the reason why this notation is super convenient, and again, if you open like any quantum computation course, you will see this notation used over and over. Is that because it kind of like takes a life of its own almost? So it's like very convenient notation. So for example, see, here's like a fun question. So what should let's write it like this. Huh? Well, yes, right. It will be like good. It would be like a tensor product of sorts. But in this case, I can give a more, which is true, but in this case, I can even give a more geometric interpretation of this. Okay, this is the fun part. Okay, so so I don't know. Let's just call this P. I'll call this P. Okay, you just have to give it a name, right? Uh, but yeah, if you kind of like go with if you go with just keeping track of everything, right? Like if you think of this as a column vector, right? This would be an n/1 column vector, right? And this is like a row vector, so it's like 1/n, right? So this would be a square matrix, right? This, like, if you just think about it, well, I mean, I still haven't actually, that's going to happen like in a moment, because like, yeah, we said like it should be. Did I mess them up? Wait, let's see. No, so this is column vector, right? So this is n/1, and the other one is row vector, so it's 1/n, right? Oh my God, yeah. Oh my God, like now see what you're saying. Yeah, like it's oh my God, I know I feel so stupid. So yeah, this is one, right, this is a column vector, so it's n by one, right? And then the other is, no, okay, why am I doing this like so, okay, no, this is, okay, so what am I what's happening here?
I thought the column vector was, the cats.
Oh, right, yeah,
You wrote.
wait, I just confused myself. The column vector is a cat. Oh, right. So this is the one that's n by one. Ah, oh my God. Thank you. Yes. Okay. Yes. Like now we're good. Right. I'm glad you caught that. Okay. So yes, we expect this to be an n by n matrix. That's where I was headed with. But what type of n by n matrix? That's what I was going to explain. Should be a square. Okay. So what is p squared? Okay. P squared should be p times p, right? Right. And this would be, just copy paste the. Is that making sense? Like that's what happens if you copy paste this, right? Huh, but now these two are next to one another. So you just merge them into like the bracket, right? So this would be like I'll put that in a different color to just emphasize that there's kind of like a merging here. Right? And okay, this is the dot product of the vector with itself, right? That's the dot product, the inner product of the vector with itself. This is the bracket. Then just, I mean, it's one if we're working with a unit vector, which I'm going to be doing just to make my life easier. So this would be one because it's the length square of the vector, right? Is that making sense? So you don't see that anymore, and so you're just left with this, like the green stuff again. But what is that? That's P again, right? So P squared equals P, right? That is a projection matrix, actually. So this is a projection matrix. It's an idempotent. So if you have ever worked with Boolean variables, right? Like x, well, 0 and 1, right? Like, x squared equals x for any, if you have a Boolean variable, where x is either 0 or 1, like x squared equals x, right? Like, so it's like the generalization of this is called like the idempotent,
So P is either a zero matrix or it's an identity matrix.
Yeah. Oh my God, you're so right about this. Wi-Fi was, who knows what will happen with today's recording, but oh, here's like a very silly example. Like just start with something very basic. Oh, should I start with the formula or with the picture? Let's start with the picture first, and then I'll explain the formula. What if I take P to be 1, 0, 0, 0? What is P squared? I claim that this is the same as P. Now, what does that correspond to? That's what I was going to show you first. This corresponds to taking a vector and projecting it onto the x-axis, right? If you look, if this is, U1, U2, right? And you look at the projection here, right? The projection is U1 comma 0, right? And the matrix that does that is this matrix P. So this matrix is really projection onto the x-axis, right? So this matrix projects onto the x-axis. Right?
Assuming that U is like vector P and it has to have that.
Oh, well, no, the vector, no, that's the thing. Like here, that's why I called it U and not V, so that you didn't think V in this vector would be the I, like, the one that you usually call I from IJK, like in this case, right? P would be,
He has instead of one and two, it wouldn't be.
well, no, but that's why I did use the fact that it was of length one, right?
Yeah.
Yeah. You do have to use the fact that it had length one. So, but yeah, like here, if you wanted to, this is E1, E1,
So if,
where E1 is like 1, 0, right?
so if you project it on the x-axis
Mhm.
and you keep projecting the projection on the x-axis,
You get the same.
you'll get the same.
Yeah. Right. And in fact, and they are orthogonal projections. They are orthogonal projections. The orthogonality means that it equals its transpose, that P equals P transpose as well. So, I mean, it's even better than just like it being an idempotent.
Oh,
So, okay. So what I was saying is that, so what I'm saying is that, so maybe I'll write it in both ways. So here's in my fancy Dirac notation, right? And here is in the traditional, like vector notation, right? Right, like so that you kind of like see it more clearly. So what I'm saying is that oh no, oh my God, I wrote it. I keep writing it. I'm terrible today with these brackets, stupid stuff. So this is how it, yeah, because you wanted like you wanted to be the tensor product, right? So it's B with B transpose. So now it's fine, right? Because now it would be n by n. So if you look at this, what I'm saying is that P squared equals P, right? And it is symmetric, right? It's a symmetric matrix, right? So any matrix, any square matrix that satisfies those two formulas properties is called like an orthogonal projection matrix. So any matrix, two conditions, a square matrix, right? Is called an orthogonal projection. Yes.
for the values of matrix P, would they only be of one or two choices out of no or not?
Oh, no, they don't necessarily have to be, no, they won't necessarily be just zeros or one. Yeah. Like it is like, because like, no, definitely. I I think I could try to come up with an example right now where it's not be that zero or one. I've already did it.
But the identity matrix also satisfies.
Right, it's a,
So what is it a projection? Like it's a projection on both the axes?
no, it's a projection onto the entire space, right? It's like the do nothing projection, right? It's kind of like an extreme case of a projection, right? Because it does not do anything.
Yeah.
So kind of like, right. Okay, so what this is saying is that you do this in linear algebra at the end when you talk about Gram-Schmidt actually, and for orthogonal projection. You do the orthogonal projection of a vector onto a subspace,
Yes,
so,
you do.
yeah. So if you have a vector, a subspace, I don't know, I'll call this subspace W of a vector space. And this is actually least squares as well, right? Like if you have a vector V, not V, I want to call it U. If you have a vector U, right? What is the projection, right? Of U onto the subspace is the orthogonal projection, right? And this in this notation, that's what I'm calling P of U. So there's like you can always find a projection matrix that like kind of like executes the projection, like that takes care of projecting the vector onto the vector space. Like in this case, you would call it W. I mean, you would call this P sub W. So this is like the orthogonal projection of U onto the orthogonal projection of U onto W. Okay.
Right. They use themselves with this like take any vector.
Well, that's what a matrix does, right? Like, its input is a vector and its output is a vector. But for a projection, you kind of like it's squared, right? So it takes a vector of the same number of entries and projects it onto, a vector of the same number of entries. But it's kind of like the shadow vector. That's how I usually call it in linear algebra. It gives you the shadow with respect to, to a vector space.
And your projection doesn't need to be on a line or.
Exactly.
It can also be on a volume.
On everything, right. So that's this one, right, is a projection onto a line, right? The line determined by the vector v, right. So it's like a special case of that. So yes, like that's that's good. That's the next thing that I wanted to say. So it's a special case of a projection of because it's a projection onto a line. So it's a projection onto the line generated by the vector v.
Would that be like
When you say would that be
projection onto a line? Would that be part of it?
Well, no, it doesn't have to be a point, right?
Oh, it could be line, yeah.
Yeah, no, like just like imagine like again, imagine the line had been the line y equals x, right? Then the vector, because I'm working with like length one vectors, it would be 1/√2, 1/√2, right? And then, oh, actually, this is a fun example. This can be done in 2 seconds. Like I think that shows you. This is like super intuitive. Okay. Yes, this is a good one. I love this example. I always do it in linear algebra when I teach it because I find the projection matrices there. And okay, this is a cool one. So I'll continue this next time because this is like a really fun topic actually. First, let's think about, it's always useful to think about okay. It's always useful to think about what the answer should be before you compute the answer, right? So I have a vector u, right? I want to project it onto this line, right? So I want to find the projection of this vector, right? What is the condition to be in this line? The condition to be on this line is that both of your entries should be the same, right? So the question is, if you have a vector with 2 random entries, for example, if you had a vector with 2 random entries like 3 and 5, how could you force this vector to be on the line? You have to force it so that its entries become the same, right? So how could you turn the entries of the vector into being the same? What's the most just way of doing that? You take the average, right? So these projections should average out the entries, right? Because that's the most democratic way of like you putting it on the line, right? So let's just check that this works. So what is a vector that gives you the vector v in this case would be, again, it has to be done like as a unit length vector. So you have to make a unit length. So it's 1/√2, 1/√2, right? And so the projection vector should be, let me use the other formula. I'll stop using direct notation for now, for a second. Because otherwise, like, I will get like messed up. And then actually that will answer your question about whether the entries also had to be always ones or zeros. Because if you do this, what do you get? 1/2, 1/2, 1/2, 1/2, right? So this is a projection matrix. Like it's a perfect average, right? It averages the entries, and that is what forces it to be on the line.
It would have been 1 or 0 if it were just the Cartesian basis.
Right, like the x-axis and the y-axis.
But
Yeah.
then
Right.
and shift, yeah.
Yeah, exactly. Yes. So, and this makes sense, right? Because if you multiply this by U1, U2, then it averages out, U1 and U2. Right.
Okay, I don't want.
And another thing, I mean, I'll put this as an example. Maybe this would be a cool example for you to work out.
So you take like a unit direction vector,
Yes.
or
A unit that, yeah, a unit vector that is the direction of the line, right, right.
but if you were to project things on a space,
Mhm.
would you take like a matrix?
Well, the formula for, if you want, I can give you the formula for the projection onto a subspace. You do Gram-Schmidt, you
Yeah.
find an orthonormal basis, right?
Yeah, like that, but that's an algorithm.
Right,
Is there like a tensor way to do it? Just like one specific tensor that does the entire.
oh, I mean, well, right, you kind of like, yeah, it's just like, it would be, yes, like, I believe,
Like take a tensor product between the orthonormal bases of their space.
if you had like an orthonormal basis for the vector space, I mean, let's call it W, right? Well, actually, this will become more clear before I give the formula. There is a formula, right, but before I give it, like, it's better, actually, it's more clear why this would be the case if you understand Boolean functions a little bit. So let's talk about the and the or, because, okay, if you have a projection matrix, what do you think the eigenvalues is symmetric, right? It's symmetric and it squares to itself, right? Anyone can take a guess on what the eigenvalues would be? Hmm? Are 1 and 0, right? Like, does that make sense? Like, the eigenvalues will be 0 or 1. I mean, I'll put that as an example for you to work it out. It's like a simple enough group. Like the eigenvalues of any projection matrix should be 0 and 1.
They're either like keeping that direction coordinate or you're just going to the.
It's kind of like that, right? Either you're decomposing that space into either you have a component, the component is in the direction of the line or like on the subspace. Like it doesn't have, either you belong to the subspace or you don't belong to the subspace and everything else is like a combination of those two.
I'm assuming you can always orthogonally decompose the matrix.
Well, I mean, they are symmetric.
Eigenvectors can have orthogonal.
They are symmetric, so they are like they use like a spectral theorem, but that's not in the direction that I was headed actually. So okay, so the projection matrix, the eigenvalues are 0 or 1 for any projection matrix. It doesn't have to be like the one that's like given by a vector. Like any projection matrix, its eigenvalues are 0 or 1. Okay, so let's see if you remember this from well, I imagine you have taken propositional calculus, right? So if you have two propositions, P1 and P2, right? When is that true? This is true when it requires both to be true, right? Like when P1 is true. Right. And in Boolean, if you use Boolean variables, right? Like, if this proposition had been represented by a Boolean variable of x1 and this one by a Boolean variable x2, right? Like that would correspond to the product x1 times x2, right? Because that's the only way for that to be 1 is if both factors are 1, right? If then entries are 0 or 1. So if you have two projection matrices and if you have two distinct projections, if P1 and P2 are two projections, which commute important fact now, because now you're in the world of matrices where variables do not necessarily, or matrices do not necessarily commute, which commute. Then P equals P1 times P2, right? Is a projection matrix, and its eigenvalue is 1 precisely when the eigenvalues for these two projections are 1. So this is a projection matrix. And it has, I mean, what I mean is like, if you had like an eigenvector that's like, I have to, I'll word it out in a more precise way on the assignment, but I'm just saying like, and, if, for example, uh-huh.
Is the commutative property like trivial?
No, like you can have projections that do not commute for sure. Yeah. Like,
So like, this is like a nice thing.
well, I mean, resist.
Oh,
And quantum mechanics is non-commutative Boolean and calculus kind of in a sense. Like, you can, this is called like quantum logic actually, where you can kind of like just extend, you can kind of like extend like the Boolean stuff to like the non-commutative case just by working with projection matrices instead, which don't necessarily commute. Hmm? Right. Yeah. More, well, I mean, yeah, it has to do with that. Yeah. Right. But it also like, well, I mean, I'm also thinking about infinite dimensional cases as well. So like, I feel, I mean, I'm saying it in a way where like, if you were in an infinite dimensional Hilbert space, like, you could still probably get away with it. Yeah. Uh, okay, we're almost done with that. I'll kind of like write it down, but all that I'm saying is that, you know, I'll add it over like to the day, like so that you can kind of like see it. So the next time you have been had like a chance to, I'll just put dot because I have to reword it in a slightly different way. But all that I'm saying is that, like the and corresponds to multiplication of matrices, and then the or, right? When you have two propositions, when is it true when at least one of them is true, right? And if you work with Boolean variables, oh, addition must to, I guess, right? Like for this, kind of like, because when is this one? It would, I think this one is fine. So this would be like P1 plus P2 minus P1 times P2, like in terms of reduction rate. So you can kind of like, I mean, I'll write this down, like, I'll write it in a nice way. Or here's another one. What is the negation, right? What is, I don't know what's the thing we use for negation. I don't remember. Like this one is true whenever the other one is false, etc. Right? So that corresponds to the orthogonal complement. No, that one.
Wait, didn't you just write like, if they have a set X1, its union with X2 will be X1 plus X2 minus.
It's kind of like the exclusion principle, right? It's similar to that idea. Yeah. But again, all of this is like kind of like you need to put like the condition that make it commute, because otherwise,
Yeah.
like that is, I mean, you can extend the formula to the thing is like if you expect, if you have done this, eh, I'm almost done with this, but like you probably know this De Morgan law, right? Like P1 and P2 or P3, right? If P1 or P2 or what? P1 and P3? No. And kind of like the idea is that if you extend this to the non-commutative case, like all these formulas collapse basically, and that's why you get all these paradoxical interpretations like of what's happening on the experiments. Because you cannot apply, like, like you have to be very careful how you apply, like, the interpretation of, like, what's going on, like, in an experiment, because like, the main point of, like, quantum mechanics is, like, the variables don't necessarily commute, like, this, certainty principle and all this stuff, so that's where, like, like, many of the classical analogies, like, break down, but I'll write that all that in a fun, as a fun exercise about projections, because it's a fun part, and then I can answer your question on Tuesday of what's the formula in terms of a tensor product, because there is one. Yeah, it's like a simple, but I just wanted to do the and or the if on the or first, and then I'll tell you how this is related to the SVD decomposition, which is still, like, I didn't have enough time, but it's a fun topic, so it's very easy to kind of go down the rabbit hole, like, one question leads to another. But let's finish here because I'm basically out of time.